In this video, we'll be looking at the design of reinforced concrete one-way slabs. One-way slab rests on two parallel supports. It can be beams or walls. As you can see, it is resting on two parallel supports. Hence, it has a bending in one direction. That means this slab has a predominant bending moment in one direction. As you can see, it is bending in this direction, and that direction is called as its direction of span. As it has significant bending moment in one direction, it has to we need to provide the flexural reinforcement along the direction of span as well. Tension is at the bottom, compression is at the top, hence we have to provide the main reinforcement at the bottom of this slab. Apart from the main flexural reinforcement, we have to provide the secondary reinforcements in direction perpendicular to the primary direction or the direction of span. The secondary reinforcements are provided in these directions. They are provided to control the cracking due to shrinkage and temperature effects. Slabs have a large surface area, therefore there can be significant evaporation of water, and hence there can be significant shrinkage in the slabs compared to the beams. Hence we have to have secondary reinforcement to control the cracking of the slabs due to shrinkage and temperature effects. One-way slab can be single span or maybe continuous over multiple spans. For example, it can be single span like this, or can have a multiple spans as well. The moments in the one-way slabs can be determined from different methods, but we'll be using a simplified method in this lectures. In the simplified method, we use moment coefficients to find out the moments at different supports depending on their support conditions. For example, if it is the support condition is shown here, we use the moment coefficients to find the moment at the supports or moment at the middle spans as well. So for example, this slab with two spans, we can have a moment m star as alpha, which is the coefficient, multiplied by FD, which is the uniformly distributed factor design load per unit area, multiplied by the clear span square, ln square. Now this alpha is given in the code in clause 6.10.2 as shown in the diagram here. For example, for the two span slab as shown in the first diagram, you will have a negative support due to some fixity at this support, and if it is simple support, the moment at 0, and there is some positive moment at the middle span and some negative moments at the middle support. So the bending moment diagram of this slab would look something like this, and the moment at this one, m star positive and m star negative. For example, the moment at the middle span here is obtained as m star. The coefficient is plus 1 by 11 multiplied by FD, which is a factor design load acting on the slab, and ln square is the clear span from the face of the support to the face of the support. This is ln. Now if we are looking at the moment, negative moment at this point, it will be m star. This one is positive, this one is negative, is the coefficient is minus 1 by 16 into FD ln square. Similarly, using these coefficients, we can find the bending moment at the supports or mid-span for different support condition as shown in the figure here. This is the shear force coefficients, and we can use the shear force formula like this one. So shear force V star would be alpha multiplied by FD ln here. So we can find the shear force at the support and at the midspan as well. So once we know the moment, maximum positive and maximum negative moments, we can design the slab accordingly. For the design of the one-way slab, we pretty much treat it as a very wide beam and with a very narrow thickness. So as you can see here, it is spanning over the supports, and it is pretty much like a beam. So we can design it like a beam. But for simplicity, what we do is, as we treat the slab, the one-way slab spanning here, as a beam of width 1 meter and the depth of ds. So we can treat this as a beam, and then we design it as a beam, and then we find out what is the reinforcement required for this 1 meter wide beam, as you can see here. And once we find the reinforcement for this 1 meter beam, then we can pretty much replicate that throughout the slab. Now, to start the design of the one-way slab, we will need to estimate the self-weight of the one-way slab. So for that, we will need the depth of the one-way slab. We will need to estimate the depth of the one-way slab, and we can use this rough guidelines as given in this design of low-rise reinforced concrete buildings from IBC. So we can use this rough guidelines to estimate what depth of the slab we should take to start designing. So we can calculate the self-weight of the slab. So from this rough estimate, we can see that for a solid one-way slab, if it is a continuous, and if it is continuous over one side, that means this is continuous in this side, but there is no continuation over this side. So if that is the case, the depth of the slab can be taken as L1 over 24, where L1 is the center distance between the supports. And if this is a middle slab, that means it is continuous in both the side. There is a slab in this side and there is a slab in other side as well. The depth of the slab can be taken as L2 over 28. And if it is cantilever, we can take it, the depth of the slab should be greater than or equal to the span over 10. So this will give us a rough estimate of what should be the depth of the slab. We should take it for calculating the self-weight of the slabs. Now, if it is simply supported slab, the initial estimation of the depth of the slab can be taken as L over 20. Again, L is the center to center distance between the supports of a simply supported one-way slab. Now, for the design of the one-way slab, we can follow these steps when we are doing the simplified method. As I said before, when we are designing a one-way slab, we'll treat it pretty much like a beam, but the beam of width B equals to 1000 millimeter and the depth as ds. So it is pretty much a very wide beam with the width of the beam or slab is 1000 millimeter and the depth of the slab is denoted as ds. So we need to find what is the reinforcement required for this wide beam spanning over the span of L. Now, to do that, we need to find out what is the design moment M star. That will be found using the simplified method as discussed earlier, using the moment coefficients. So we can find out what are the positive and negative moment for the slab, and then we have to design the reinforcement for both positive and negative moments as well. Now, once we know these moments, design moments, then we can estimate what is the reinforcement required for this 1000 millimeter beam. So we'll be finding what is the area of reinforcement that has to be distributed throughout this width of the slab. So to estimate the area of reinforcement, we'll assume that the lever arm, the depth of lever arm, that is the distance between the tension force and the compression force in this slab, is Z equals to 0.9 D. Using the same equation as we did for the beam, we can estimate what is your design moment capacity using M star equals to phi mu. Therefore, phi mu is T multiplied by the lever arm Z, where T is the area of reinforcement distributed over the width of the slab, that is 1000 millimeter, multiplied by the tensile strength of the steel, FSY, if it is already yielding, and Z we approximated it as 0.9, the effective depth of the slab. With this equation, we can find out what is the area of reinforcement required when we know the maximum positive and negative bending moment. So now, simplifying this equation, we can find out area of reinforcement required is M star over phi FSY 0.9 D. So from there, we can estimate the area of reinforcement required for both positive and negative bending moments separately. Now, to ensure that the slab doesn't fail immediately after cracking, we have to make sure that we provide at least the minimum amount of reinforcement, and clause 8.1.6.1 gives us the minimum amount of reinforcement as AST means for the slab. So we have to make sure that whatever area that we calculated and we provide for the slabs should be greater than at this as given in this equation. In this equation, F-CT.F is the characteristic flexural tensile strength of the concrete, which can be obtained based on the compressive strength of the concrete. Now, once we calculate the area of the reinforcement, we provide the area of reinforcement, we need to check whether that area that we are providing should be at least greater than the minimum area required as prescribed in 8.1.6.1. So once we have the trial reinforcement area, AST as calculated before, we need to find out the spacing of the reinforcement. Now, as we are considering the slab as the beam of 1000 millimeter width, so we have the reinforcement distributed over this 1000 millimeter width, and the area of reinforcements as we calculated AST, and we have considered that the spacing between the reinforcements here is S, and the area of one bar is denoted as AB, then we can find out the distance between the spacing between the reinforcement as 1000, because it is 1000 millimeter beam, multiplied by area of one bar divided by the area of reinforcement calculated for this whole section. So that will give us the spacing between the bars. Now, we are doing this for 1 meter slab, and once we have the spacing, we just have to repeat it over the length of the slab. Now, once we have this trial area and trial spacing, we have to make sure that the design moment capacity is greater than M star. So what we are doing is finding out the design moment capacity per meter width, because we are doing the slab design per meter, is greater than or equal to the M star, the maximum design negative or positive moment per meter. So once we do the design check for the moment capacity, we need to check for the shear capacity as well. Usually for the slabs, we do not need to provide the shear reinforcement, but we need to check and make sure that the shear capacity is adequately satisfied as well. So for that, what we need to do is we find out the maximum shear forces on the slab using the coefficient method as shown before at both the supports and the midspan as well. And then we find out the shear capacity contribution from the concrete per meter width and make sure that it is greater than the shear force at the supports and the midspan. Apart from designing the slab for bending moment, we have to make sure that whatever reinforcement that we are providing in the primary direction should meet the crack control criteria as well. The aim is to have smaller cracks, many cracks, rather than having a big, large crack. Now, for the crack control perspective, the primary reinforcement that we calculate AST for the primary direction or the direction of the span has to meet these criteria given in clause 9.5. The first one is that, as we discussed earlier, whatever the reinforcement area that we are providing, AST, has to be greater than the minimum reinforcement as given in clause 8.1.6.1. So the area of reinforcement that we are providing over the slab in the primary direction as we discussed earlier. So we are designing the primary reinforcement for the slab of width 1000 millimeter. So this reinforcement that we calculate AST should be greater than AST mean provided by this equation. Second condition is that the center to center spacing of bars in the primary direction should not be greater than 2 times the depth of the slab or 300 millimeter. So center to center spacing of the bars in the primary direction is denoted by S. So S shouldn't be greater than 2 ds or 300 millimeter, whichever is smaller. So that will also help to control the crack in primary direction. And the third condition is that the primary steel that we are providing in the direction of span should be at least 75% of the secondary steel that we are providing in the perpendicular direction. As discussed earlier, secondary steel we are providing to control the shrinkage and temperature effect cracks. And the primary reinforcement that we actually designed for the bending moment should at least be 75% of the secondary reinforcement. As you can see from this condition, you can see that the secondary reinforcement that we are providing for the crack control or from shrinkage and temperature effect can actually be bigger than the primary reinforcement. That can be a governing factor, but we have to make sure that the primary reinforcement that we are providing for bending should at least be 75% of the secondary reinforcement that we are providing for shrinkage and temperature effects. Now that's for the primary steel crack control requirements. But apart from that, we also have to provide the secondary reinforcement in perpendicular directions. So looking at the slabs here, so for the secondary steel that we are providing in perpendicular to the direction of span, we have to make sure that we are providing adequate steel to control the cracking due to shrinkage and temperature effects. So it is governed by clause 9.5.3.3 to 9.5.3.5 based on their restriction conditions for the slabs. So to control cracking due to shrinkage and temperature effects, minimum reinforcement should be provided in second direction as well. A minimum reinforcement in second direction is given in these clauses. Now, if you look into these clauses, there are a couple of things to note here. So if the secondary direction is unstrained, so if the slab is free to expand in the secondary direction, then the minimum amount of steel that we need to provide in secondary direction, that means the AST in the secondary direction, should be at least greater than or equal to 1.75. Now, if it is a pre-stressing steel is not there, then it will be 0. So if there is no pre-stressing in the slabs, this becomes 0. So it will be BD into 10 raised to power minus 3. So this will be the minimum area of reinforcement that we need to provide in secondary direction if the slab is free to expand in the secondary direction. Now, if the slab is restricted in the secondary direction, that means secondary direction is restrained slab, then we can find out the area of reinforcement in secondary direction based on what level of crack control is desired. Now, for example, if the minor degree of control of cracking is required, that means the crack control is not that severe, then the equation is as same as before. It's 1.75 BD 10 raised to the power minus 3. And if the crack control we require is a moderate degree of crack control, it will be 3.5 times BD into 10 raised to the power minus 3. And if it is strong, quite stringent crack control criteria, it can be 6 BD into 10 raised to the power minus 3. So this will give the minimum secondary reinforcement required for slab fully enclosed within the building. Now, depending on the exposure condition, if it is A1 or A2 exposure, we can find out the secondary reinforcement from here. And if it is B1, B2, and C1, C2 exposure condition, we can find out the area of reinforcement in secondary direction from this equation. Now, for the detailing of the slab, we need to provide the cross section and also the plan view as well, as you can see. So these are the support, and this is the direction of span of the slab where there is a maximum bending moment occurring. So the bottom reinforcement, this one, is the main flexure reinforcement, the primary reinforcement, and on the plan view we can see that this one is the primary reinforcement. That means this black one here, the arrow means that from here to here, wherever the length of the slab is, we are providing N12 bars, diameter bars, at 220 center to center. So, and B1 means the bottom layer. It is from 220 center to center. We are providing N12 bars from here to the end of the slab. Now, the secondary reinforcement is perpendicular to that primary reinforcement. So it is provided in this direction. And in this view, we can see that the secondary reinforcements are noted as here. So these are the secondary reinforcements. And from here to here, the secondary reinforcement we provide are N12, 190 center to center. So this is just an example. So just to note how we can do the detailing of the slab.